We already touched on parameterizations a couple of times, but somebody asked specifically whether I can say something about this book. So I'm just going to add maybe two podcasts from this. It's specifically on parameterization schemes, keys to understanding numerical weather prediction models. David Stensrud. I'm not going to obviously go through the whole book, but I picked a few key figures to make some additional points and re-emphasize some of the points we already made. So the idea of resolution comes out very clearly in this nice figure, which is showing a satellite view of a field of cumulus clouds at 1 kilometer resolution forming over Louisiana and Mississippi. So you can see the Gulf of Mexico here and the states over there. Open white polygons represent different sizes of grid cells varying from 160 kilometers on a side down to 5 kilometers here. Even within the 5 kilometer grid cell, there are cumulus clouds smaller than the grid cell. Satellite image courtesy of National NOAA. So the idea is again that when we do modeling with such large coarse resolutions in the horizontal, of course also vertical resolution will affect the processes themselves. We are talking about parameterizations at multiple levels. One is, as we said before, we don't have a complete process understanding of the clouds, so often the details of how clouds are formed, different types of clouds, how clouds precipitate, the instability processes that initiate the process of convection and cloud formation, surface-based convection, elevated convection, tropical, mid-latitude, lots of details, but satellite data themselves often also can have limitations in terms of their resolution. And satellite data is not like it's you have a particular channel that measures only clouds. You have to take radiances that are coming from the surface or the atmosphere in various spectral bands, or you have active signals like lasers shooting down and coming back and so on, or radars flying around, which are all used with various levels of corrections to extract the data. So here cumulus clouds at 1 kilometer resolution basically means there is an intrinsic resolution of the satellite, and the gridding, taking satellites fly in certain configurations, taking them and stitching them together into grids like this itself is an art form as well. So there is the process understanding, which requires parameterization. There is comparison to satellite data, which requires various ground-based data to make sure that the satellite is well calibrated and validated, and so on and so forth. And then there are all the other detailed processes of dynamics that matter as well. Keeping all that in mind, then look at idealized vertical column of a model grid cell. N vertical layers here, and vertical layer N is highlighted here. So we have soil layers here in the black, which we will look at in a bit more detail. Vertical layers, radiation, convection, microphysics, planetary boundary layer, turbulence, orographic drag, and vegetation, and or bare soil and or water. So it could be ocean grid, lake grid, etc. Parameterizations are likely to affect the model variables as indicated. So many details are not explicitly written in terms of equations, so they are parameterized. Vegetation is often not modeled, and if it is prescribed from observations like satellites, then satellite derived vegetation index like leaf area or normalized difference vegetation index and so on themselves are derivations from various measurements from satellites, which include assumptions and approximations. So there is convection, microphysics, there is radiation, turbulence, orographic drag, planetary boundary layer, which requires a certain vertical resolution, which is not always there in the models. So there's infinite details that obviously we are not going to go into, but it gives you a sense that models have primitive equations for momentum, as we saw, thermodynamics, mass conservation, there is thermodynamic equation, and so on that we are using along with these parameterizations. So here is an example, a mountain ridge near Fort Collins, Colorado, illustrating the vegetation contrast on a south-facing slope on the left side of the ridge here, which is obviously in the rain shadow, and here is getting more rain, so you can see a stark contrast between vegetation and hence soil types and surface roughness, boundary layer, cloud microphysics, etc. And here is the leeward side, so you can imagine that this scale here is much smaller than most of the global weather or climate models, and even when you do regional climate models, depends on the resolution at which these are resolved, and the resolution cannot increase infinitely because some of the assumptions made on turbulence can fail when you go to let's say less than half a kilometer resolution, so they won't work at 1 meter resolution, for example, so you'll have other problems to deal with. Terrain field over the island of Hawaii represented using 30 kilometer, 10 kilometer and 5 kilometer grid spacing. You can see the details that get resolved as you go to higher resolutions, and as always, remember, even 5 kilometer is grossly inadequate for many features of the atmospheric circulation and weather phenomenon. Terrain heights are shaded every 400 meters in parallel lines here. Note the much greater terrain details as the grid spacing is decreased, as well as the increase in maximum terrain height as indicated by the greater number of alterations in shading. At 30 kilometer, the highest terrain point is 1892 meters. That's all you are resolving. Whereas at 10 kilometers, it's 2974 meters, and at 5 kilometers, it's 3918 meters. So you are making a massive difference in the representation of the orography, which means the flow is going to be different, the amount of rain is going to be different, downstream effects are going to be different, the waves generated by the flow propagating far into the mainland of US, for example, are going to be different as well when you change the orography so much. The actual peak of Mauna Loa is at 4,169 meters, which you are missing anyways. Also note the northern displacement of the highest mountain terrain in A compared to B and C. So highest terrain is here, whereas you are splitting it and moving it around at higher resolutions. Okay. In addition, the northern peak of Mauna Kea, 4,205 meters, is seen using 5 and 10 kilometer grid spacing, but is not seen here at all. Finally, the Kohala Mountains, stretching southeast to northwest along the northern tip of Hawaii, are clearly seen here, whereas they are basically missing here. Okay, so all these kinds of things matter, and even on the land surface parameterizations, time series from January 1998 through September 1999, which was going through the end of the strongest El Nino of the 20th century, one of the strongest, through September 99, which was one of the strongest La Niñas of the century as well, which has an impact on on Oklahoma's weather and climate. Spatially and vertically average soil moisture in Oklahoma values are from observations, which is shown here in this this thin line here. And 4 land surface schemes forced by the North American LDAS, which is the Land Data Simulation System, which is a merging of the model and the data to provide the best interpolated data we can get for a certain period, dynamically interpolated. Soil moisture is for the top 40 centimeter layer. The schemes used are Mosaic, NOAA, Variable Infiltration Capacity, and Sacramento. There are details that are different in each model. They are designed based on different requirements, different processes, different data sets, different goals, different process understanding requirements, and so on and so forth. But you can see the deviations from the observations and the differences among models. We have seen this kind of thing before, and we also seen that when we look at future projections or past performances of models in the IPCC class models, precipitation is always a nightmare, which is much smaller scale than temperature. And now imagine the soil heterogeneity and soil moisture, which is going to be even smaller scale than rainfall, even though rainfall is often integrated to produce soil moisture variability and so on and so forth. So parameterizations going into the models are different, and obviously the outcomes are different. So we have to worry about all these things in reality, and we have to be aware of what we are dealing with so that we interpret the results very carefully. Oceans have similar problems in terms of how the momentum penetrates, how solar radiation penetrates, how evaporation, precipitation affect salinity, stability, energy exchange with the atmosphere, how rivers come in, and so on. Here's an example of the problems with the data itself. So the distribution of AVHRR daytime, one of the satellites, advanced very high resolution radiometer, and daytime and nighttime retrievals within 1 degree latitude longitude grid cells for the week of 4 to 10 August 1991. A dot indicates 1 to 9 observations are present within a grid cell, while an X indicates 10 or more observations. This is from Reynolds and Smith, which used to be one of the most used sea-surface temperature products, which was used for validating models, for forcing atmospheric models, for studying processes, and so on and so forth. But the idea is, you can see that the daytime and nighttime there are big differences in terms of the number of data available. There are large data gaps, as well as differences in the amount of data per grid cell. So you can take these and make calculations of signal to noise ratios in the data itself. Okay, so one has to be aware that data that we are using also have severe limitations because of resolutions and so on. So let me leave this podcast here and come back and cover some of the other aspects of convection, convective parameterizations, and some of the issues involved in there in the next podcast. Again, remember, this is a very, very brief introduction to some of the issues of parameterization. This book has some 300 pages of details of land, ocean, atmospheric processes, convective parameterizations, and future directions, and so on. So definitely worth reading if you are into parameterizations or improving them and so on. This is just a brief introduction for those who are just trying to get a broader picture of modeling and parameterization. Okay.